Okay, this is the lab on air resistance. So in this experiment, we're going to be dropping these coffee filters, and we're going to measure the effects of air resistance. Okay, so what we're going to do is look at specifically terminal velocity. So when we have an object falling, we have the force of gravity acting downwards, and we have a force of air resistance acting upwards, which in previous experiments and subsequent experiments we will normally ignore air resistance, but this is going to be the focus of this experiment. So as it accelerates downwards, although the force of gravity being constant, the force of air resistance is not. It will increase as the speed increases. So as it accelerates downwards, it goes faster and faster and faster, so the force of air resistance gets larger and larger and larger. And there comes a point where the force of air resistance equals the force of gravity, and that's at that speed we call that terminal velocity. So in general, we can look at Newton's second law, and we can see that the sum of the forces, the force of gravity, if we have downwards as positive, minus the force of air resistance acting upwards equals mass times acceleration. So that's true whether it's at terminal velocity or not. But at terminal velocity, we said it stops accelerating and it moves at constant speed, since the force of gravity equals the force of air resistance. So our acceleration is 0 at terminal velocity. Okay, so we set that equal to 0, so we know that the force of gravity in that case, that special case, is equal to the force of air resistance. So the force of gravity can also be described as its weight. So weight in newtons, mass times the acceleration of gravity, mg. Now we're going to use this model that's given to us to calculate the force of air resistance. We're given this model that the force of air resistance may be approximate to some constant times the times the velocity to some power, whether it's terminal velocity or not. Now this is kind of this is just a crude approximation. We're ignoring air viscosity and other factors as that in this model. Okay, so this is purely related to the velocity. So we can set that equal to mass times gravity, mg. All right, so now we have something to work with. What is our goal? Our goal is to find terminal velocity and use that to figure out what model is going to work best. Which value of n is going to best describe our data. So we're going to look at n equals 1, n equals 2, and n equals 3. So we're going to say, is the force of air resistance, is it more equal to some constant times velocity, some constant times velocity squared, or some constant times velocity cubed? So we have three possible models. Now you can hypothesize which one you think might be best, and that's something you can look at on your lab report if you're doing a formal report. And whether in any type of report that can be discussed in the conclusion, partial or formal. Okay, so which one of these is going to be best? That's kind of going to be our goal of the experiment, and we'll determine that graphically. Okay, so let's do a trial here to collect our data, and when we collect our data, Logger Pro, our software, is going to be looking at a position time graph. Okay? Now, I drew kind of an approximate scenario here. So on a position time graph, of course we know the slope at any point is our velocity. So here our slope is low, so we have a low velocity. So this is for an object falling. Well, here we have a little larger slope, so the velocity is larger, and here the velocity is even larger. So this shows that an object is accelerating. Okay, the curvature on a position time graph. Okay, so we have an object falling that's accelerating. And our terminal velocity point, what do we expect that to look like? Well, at this point here, now we have a constant slope after that. That means we have a constant velocity. If velocity is constant, therefore acceleration must be 0. So this portion of the graph represents our terminal velocity. Up here it does not. Okay, it's still accelerating, then the acceleration stops. Remember, it's a position time graph. So you can review those if that's hard to interpret. Okay, so that's what we kind of expect to see on our program. So let's do a trial. And here we have our position time graph set up. We have our motion detector. And we have these coffee filters that we're going to use. Okay, so I'm going to attempt to do this. Okay, so we got something here. This portion of the graph looks good. This spike means it just went out of the range of the motion detector. And this is before we started collecting. So let me try one more time. Same issue here. So I'll see if I can get some good data.